any questions first? Now, there's just one thing left that I would like to do. That is called the covariant formalism. Now, what we mean by covariant formalism will be, special relativity tells us that the space and time, they should be treated on a similar footing, let's say, not exactly identical, but on a similar footing. But if you look at the Maxwell's equations, we have del dot E is equal to 0, del dot E is equal to rho over epsilon 0, curl of E is equal to minus del B by del T, curl of B is equal to mu 0 J plus mu 0 epsilon 0 del E by del T. Okay, the time and the position derivatives, they don't appear symmetrically. Now, furthermore, if you look at the fields, now we had defined this concept of space-time, which is four-dimensional space. But you see the electric field or the magnetic field, they just have three components. There is no fourth component to the electric and magnetic fields. And when we looked at the transformation properties of the electric and magnetic fields from one reference frame to the other reference frame, we had seen that we cannot even treat them as part of a four vector. And we will see today that they are actually what we call rank 2 tensors. Okay, now again this puzzling word tensor, don't get confused. Now what we had written, we had said that the position can be written as a four vector in this form. Ct will be the zeroth component, and the position space coordinates of the position is the space components, and this thing we called x mu. And then we said that, okay, the Lorentz transformation of these objects is Ct will be transformed into gamma Ct minus beta x if the reference frame they are moving, the second reference frame is moving in the x direction. And x1, Ct, by the way, we denoted it as x0, so this is x0. X is just x1. x1 just becomes gamma x1 minus beta x0. And x2 doesn't change, x3 does not change. And we said that all these four laws, we can actually write them in the form x mu. This will be transformed into x prime mu, which we said that we can write as this matrix product. So here you should understand this as a matrix product. This is the column index. Let's multiply with the row index. This is the row index of my matrix. And in fact, then we said that if we have any four quantities, let's say V mu, and if they transform in this way such that V mu, if you go to the new reference frame, it will become V prime mu, the new components, lambda mu nu, V nu, then V mu is a four vector. Just like in ordinary three-dimensional vectors, we define any quantity of vector, we call it any three numbers a vector if when you go from one coordinate system to the other coordinate system, they change just like the position vector. So here, the position vector gets transformed by this matrix lambda. So if you have any four numbers that are transformed just exactly in the same way, then we call that a 4 vector. Well, we can also talk about the products of different components of these 4 vectors. V1 mu, V2 nu. This is something. We had already seen an example where we are multiplying different components of vectors. If you remember the Maxwell's stress tensor, we were multiplying, let's say, the x component of the electric field with the y component of the electric field. So it's just made up of terms of this form. And if we just give them a name, let's say T mu nu, what happens to them when I go to a new reference frame, which was V1 mu, V2 nu. In a new reference frame, this just becomes V1 prime mu, V2 prime nu, which I can write as lambda mu alpha, V1 alpha, lambda nu beta, V2 beta. Or T mu nu, under a change of reference frame, it just becomes T prime mu nu, which is lambda mu alpha, lambda nu beta, T alpha beta. So basically, each one of these indices, they just transform with one of these lambdas. I mean, whenever you see a tensor, you can always think of it as the products of different components of vectors, or sum of terms that can be written as the products of different components of vectors. That's basically what the tensor is. Now let's see how they transform from one reference frame to the other one explicitly. This is the law that allows us to obtain the transformation properties. Let's see, T prime 0, 0. This will be lambda 0, 0, lambda 0, 0, T 0, 0, plus lambda 0, 1, lambda 0, 0, T 1, 0, plus lambda 0, 0, lambda 0, 2, lambda 0, 0, T 2, 0. Well, we have many terms. Basically, in the sum, if you just write it out explicitly, you will have 16 terms. Let me not write them out explicitly. Let me make some shortcuts. Now, let me just consider a tensor which has this property. For example, it can be V1 mu, V2 nu, minus V1 nu, V2 mu. If you look at that tensor over here, it's written as a combination of the products of components of vectors. But I take such a combination that if I change mu and nu, the first term becomes the second term becomes the first term. So if I change the positions of mu and nu, this term acquires a minus sign. Well, the nice thing about such tensors is they have fewer components. That is what will save me. Well, the diagonal components, they have to be 0. Here I have T1, 0, minus T1, 0, T2, 0, minus T2, 0, T3, 0, minus T3, 0, T2, 1, T3, 1, T3, 2, this is here, minus T2, 1, minus T3, 2, T31, T32 minus. So you see it only has 1, 2, 3, 4, 5, 6 independent components. The other 6 non-zero components are just minus these ones. This is kind of nice. I have 3 components of the electric field, 3 components of the magnetic field. So somehow I might be able to manage to put all the 6 components of the electric and magnetic field in such an antisymmetric tensor. There is nothing new. Okay, now let's go back to how this tensor will transform as I go from one reference frame to the other one, T prime 0, 0. This will be lambda 0 alpha, lambda 0 beta. T alpha beta. And keep in mind that lambda 0, 1 and lambda 0, 0, these are non-zero, with the top indices being 0. These are the only non-zero components. All the other, if alpha is 2, alpha or beta, if they are 2 or 3, they are all 0. And since this is antisymmetric, alpha and beta has to have different values. They cannot be both 0, they cannot be both 1. So this sum is nothing but lambda 0, 0, lambda 0, 1, T 0, 1, minus plus lambda 0, 1, lambda 0, 0, T 1, 0. So I don't have many terms. There are just 2 terms in that summation. Questions?
How did you write the components of the matrix?
You see, this is T mu nu. This is the mu index. This is the nu index. So this row is mu is equal to 1. This is mu is equal to 2. Oh, sorry, this is mu is equal to 0, mu is equal to 1. 1, 2, 3, okay. Okay, so let me see. So this is the second index, nu is equal to 0. This is nu is equal to 1. No, okay. Maybe this way it will be easier to see. Okay. This is mu is equal to 0. This is mu is equal to 1. But you see, if I change the T02 is minus T20. So that's why I just switched it. This is mu is equal to 1. This is mu is equal to 2. This is mu is equal to 3, this column. This row is nu is equal to 0, nu is equal to 1, nu is equal to 2, and nu is equal to 3. And the entries, since it's antisymmetric, the entries over here and over here, they are related by a minus sign.
So why is the diagonal component 0?
Well, let's see. T00. If I exchange the first and the second index, this is antisymmetric, it should acquire a minus sign. So T00 should be equal to minus T00. So T00 should be 0. Similarly, T11, just change the places of those ones, it should be minus T11. So a number is equal to minus itself, that number has to be 0. And then, okay, I just looked at how the 0, 0 component changes if I, oh, sorry, I made a stupid mistake. The 0, 0 component is 0 anyway. Let me look at how the 1, 0 component is modified as I go from one reference frame to the other one. This is lambda 1 alpha, lambda 0 beta, T alpha beta. Now, and remember, this lambda matrix is this one. Gamma minus gamma beta minus gamma beta, gamma 1, 1, all zeros. So if I'm looking at the first row, not the 0th row, but the first row, alpha can be only 0 or 1. In the 0th row or column, beta can be 0 or 1. Alpha or beta, they cannot be more than 1. They have to be 1. Furthermore, if alpha and beta equal, this is 0. So alpha and beta, they can be either 0, 1 or 1, 0. And I don't have any other term in that summation over alpha and beta. So this will be equal to lambda 1, 1, lambda 0, 0, T1, 0, plus lambda 1, 0, lambda 0, 1, T0, 1. Okay, the 1, 1 entry of lambda is gamma. Similarly, 0, 0 entry is just gamma. So this is just gamma squared. T1, 0 plus 1, 0 entry and 0, 1 entries are minus gamma beta. So that is plus gamma squared, beta squared. T0, 1 is minus T1, 0. So T prime 1, 0 entry under a Lorentz transformation, it becomes gamma squared 1 minus beta squared T1, 0. But gamma squared is nothing but 1 over 1 minus beta squared, so they just cancel each other. So nice. The 1, 0 entry of this symmetric matrix does not change. If I go from a reference frame to a different reference frame, which is moving in the x direction. Well, I'm just looking at an anti-symmetric matrix. This is not symmetric. I'm looking at not a symmetric one. It's an anti-symmetric one. Why am I looking at an anti-symmetric one? Well, I know that it will work. Yeah, another motivation for taking an anti-symmetric matrix is if you take a symmetric matrix, it has 10 independent entries. The diagonal ones are independent. The ones above the diagonal depend on the ones below the diagonal, so I only have 6 independent elements above the diagonal plus 4 elements along the diagonal. I have 10 entries. So what are they? When I'm looking at the electromagnetic field, I only have 6 independent fields, not 10. But if I look at an anti-symmetric tensor, the anti-symmetric tensor has only 6 independent components. 3 components, I mean, it's just up to this point, at this point, it's just a guesswork. I'm saying that, okay, I'm trying to write down a covariant formalism in a 4-component notation, and I have to find some object which will contain my electric and magnetic fields. The first guess would have been, okay, I would have imagined, okay, I have the 3 components of the electric field, just let's add the 0th component and it will become a 4 vector. But we had seen that it doesn't work because if I go from one reference frame to the other reference frame, electric field and magnetic field, they just get mixed up. 4 vectors do not get mixed up with other objects. So now, since I'm getting these 3 components of the electric field and 3 components of the magnetic field, they get mixed up under a reference frame change, I have to look for some other objects which contain all of these. The next choice would be a generalization of the vectors, which we call the tensor. It's just the products of, the tensors, you can just think of them as the products of different 4 vectors. And that allows you to determine how they transform from one reference frame to the other one. But I have only 6 fields. So I have to find a tensor which can contain only 6 fields. And it turns out that an anti-symmetric rank 2 tensor has 6 independent components. So the guess would be I should be able to put my electric and magnetic fields, I might be able to consider my electric and magnetic fields as the independent components of this anti-symmetric tensor. But of course, if they form the components of an anti-symmetric tensor, the transformation laws for the electric and magnetic fields should match the transformation properties of a rank 2 anti-symmetric tensor. So now that's what I'm trying to figure out. I'm trying to first figure out how my tensor, rank 2 the components of my rank 2 tensor, they change from one reference frame to the other reference frame. That's what I'm trying to figure out. And then what I will do is I will just compare it with the transformation properties of my electric and magnetic fields and try to see if they match or not. At least for the time being, there is hope. You see, if I'm moving in the x direction, T10 entry does not change. And when you look up the transformation properties of the electric and magnetic fields, if you go to a reference frame which is moving in the x direction, the x component of the electric fields do not change. Well, neither the b component of the electric field. None of them changes. So I can identify T10 with either the x component of the electric field or the x component of the magnetic field, for example. Sorry. Now let's look at the T20 component. How does it change as I go from one reference frame to the other one? This is lambda 2 alpha, lambda 0 beta, T alpha beta. Well, if you remember the form of the lambda matrix, alpha has to be 2. Only lambda 2, 2 is non-zero. The other entries, lambda 2 alpha, they are all 0. Lambda 2, 2, lambda 0, 0, T20, plus lambda 2, 2, lambda 0, 1, T21. So the 20 component of my tensor becomes, well, gamma 22 is 1, gamma 00 is gamma, T20 minus beta gamma, T21. Is the YT component. Well, again, if you go back to our identification, our Lorentz transformations, these look similar to these ones. EY prime is equal to gamma EY minus beta CBZ or BY, well, here I have a beta. Well, it looks like this one. Of course, I need to identify T20 with EY and T21 with C times BZ. If I make that identification, then this transformation property is exactly this one. Well, it also looks similar to this one. CBY prime is equal to gamma CBY plus beta EZ. Well, I can say that, okay, T20 is CBY and T21 is just minus EZ. Then again, I get exactly the same transformation property. And well, you can just continue like this, see how the 6 components transform. And it turns out that there are 2 possibilities. Well, let me just use this notation for my tensor F mu nu, which will contain my electric and magnetic fields. And the components are this one. You can just look it up in your book. The diagonals are 0, Ex over C, Ey over C, Ez over C, 0, Bz, minus By, 0, Bx, and 0. Well, below the diagonal is just antisymmetric. This is one choice. Well, the other choice is this one. Zero, Bx, By, Bz. 0 minus Ez over C, Ey over C, 0 minus Ex over C, 0. Well, it's not a big deal, great surprise that we ended up having two possible tensors which can contain our electric and magnetic fields. Because if you look at the equations, the Maxwell's equations, well, at least in the case that rho and j is equal to 0, if rho is equal to j is equal to rho is equal to 0, j is equal to 0, and curl of E is equal to minus del B by del T, and instead of that mu 0 epsilon 0, let me just write 1 over C squared. Well, they look quite symmetrical. You see, if in these equations, let's say instead of B you just put E, and instead of E you put minus B, nothing changes in our equations. And if you look at these two tensors appearing over here, how do you get G from F? Well, instead of E, just put B. Instead of B, just put minus E, or with certain factor C. So the existence of two possible tensors is basically a reflection of the fact that the Maxwell's equations are almost, not exactly, but almost symmetrical between the exchange of the electric and magnetic fields. This is called the field strength tensor. And G mu nu is called the dual field strength tensor. Yeah, it's just a terminology. Both of them are used. Now, okay, so fine. Now we have a tensor in which we could just put all our Maxwell's fields, the electric and magnetic fields. But what about the Maxwell's equations? So basically what we want to do is we want to write everything in a form in which the time and the position, they appear in a symmetrical fashion. So this was part of our job, to be able to find a way to represent the electric and magnetic fields. But the other part is, what about the equations? We have the Maxwell's equations. How will we be able to write the Maxwell's equations in terms of these tensors? Well, one hint You see, these tensors basically they are 4x4 matrices. You see here, 3 equations plus 1, we have 4 equations, if you like. 3 equations here plus 1, 4 equations there. So that is also nice, at least things seems to, we are in the 4-dimensional space-time and kind of we know how to combine these objects. Now let me look at these objects. This is what I would like to look at. Let's start with nu is equal to 0. Now keep in mind, if nu is fixed, I'm looking at the first row. If it is 0, I'm looking at the 0th row, the first one. So if 0, 0 is 0, f1, 0 is minus ex over c, f2, 0 is equal to minus ey over c, f3, 0 is minus ez over c. Del x mu, this will be del f0, 0, del x 0 with a minus sign, plus 1, 0, del x 1, del f2, 0, del x 2, del f3, 0, del x 3. And that minus sign is basically because of the fact that when we had 2, 4 vectors, we define this as minus a0 squared plus a squared. This minus over here and this minus over here, they are the same minus. Well, it doesn't really make too much of a difference if 0, 0 is 0 anyway. But you see, look at over here. F1, 0 is ex, x1 is x. We are taking the derivative of ex with respect to x, taking the derivative of ey with respect to y. We are taking the derivative of ez with respect to z. This is nothing but minus 1 over c divergence of E. So del f mu 0 over del x mu is minus rho over c. 1 over epsilon 0. The first one. Well, f0, 0 is 0. So the time derivative is 0. F0, 0 is 0. Because it's antisymmetric. All the diagonal entries are 0 all the time.
Hocam burada elektrik alan zamandan bağımsız mı?
We are not saying that. We are just saying, we are not saying that the time derivative of the electric field is 0. We are not saying that. We are just saying that the 0, 0 element of F is 0. And 0 is independent of time. I'm not saying anything about the time derivative of the electric field. It doesn't even appear here. This is my first Maxwell's equation, written in terms of this F mu nu, the Gauss law. Now let me look at the nu is equal to 1. And then we can give a break. Well, let's see. F10 F10 is Ex over C. No, sorry, F01. F11, this is 0, because it's a diagonal element. That's why F11 is 0. F21, this is minus Bz. F31, this is equal to By.
Minus B by
F31. You see, mu is 1. So I'm looking at this row. F31 is this element over here, which is minus this element. So let's see, F mu1 derivative with respect to x mu. This is F01 derivative with respect to x0 with a minus sign, plus the derivative of F11 with respect to x1, plus derivative of F21 with respect to x2, plus the derivative of F31 with respect to x3. This is equal to, now F01 is E over C. So this is minus 1 over C squared dEx by dt. Well, x0 is C times t. That's why I have the derivative with respect to x0 is 1 over C times the derivative with respect to t. And there is another C in F01. Sure, I will write all the other terms. This is just the first term. You see, I'm just writing the terms of f explicitly. This is my F10, which is Ex over C. So wherever I see F10, I can just write Ex over C. Now this is just this term. F01 is Ex over C. I'm just taking its derivative with respect to x0, and this is what I obtain. F11 is 0. So the second term is 0. Well, F21 is Bz, x2 is y, F31 is by, and x3 is z, which is equal to minus mu 0 epsilon 0 dEx by dt plus the curl of B, the x component. Yes, that's T. And Maxwell's equations tells me that this should be equal to mu 0 times Jx. So here I have my new Maxwell's equation that F mu 1, well in fact 1, 2 or 3 that x mu, this will be equal to mu 0 j x, y or z, whichever one you take.
Hocam mu'de sıfırdan ulaşması gerekmiyor mu? 0, 1, 2, 3.
You see, 0 we had calculated separately. Now let me just check one thing. So what is the x component of curl of B? the x component, this is del bz by del y minus del by del x, del z. So this is minus over there. That is minus mu 0 jx. Well, I should have a plus sign over here. Let's just, I made some mistake in the sign somewhere. This should be plus if you do it properly. And so here you will get a minus sign. Because you see, curl of Maxwell's equation tells me that curl of B should be mu 0 J plus this thing.
What is the first term negative?
Which one?
Minus 1 versus, no, minus del F.
This one. Well, let me see.
Aslında o eksiği içermiyor mu kendi için? Hani eksi ct diye düşünüyorsun.
You see, when we have a mu, b mu, this is minus a0, b0, plus a dot b, or a0, b0 plus a dot b. Now, del over del x mu, f mu nu, this is equal to, f0 nu del x0 plus del f I nu del xi. Yeah, there's no minus sign there. Let me also correct here, there's no minus sign here. There's no minus here, no minus here. This is plus. Okay. Now we have, okay, let's go back to the Maxwell's equations. Okay, we have this Maxwell's equation. We have this Maxwell's equation written in terms of f mu nu. What remains is these two equations. And for those two equations, we will basically use G mu nu, the dual tensor. So this is my dual tensor. Let me just pick it up. Now let me calculate derivative of G mu 0 del x mu. I'm just repeating basically the same thing, but this time with the G matrix. This will be equal to, well, G00 is 0, G010 is minus bx, G20 is minus by, G30 is minus bz. Written explicitly, this is G00 by del x0 plus G10 del x1 plus del G20 del x2, G30 del x3, which is nothing but minus the divergence of B, which would be 0. Okay, this is our third Maxwell's equation. Let me look at the other ones. Mu1, del x mu. Now I will look at the first row of G. G01 is Bx. G11 is 0. G21 is Ez over C. G31 is equal to minus Ey over C. So this is equal to derivative of G01 with respect to the x0 plus derivative of G11 with respect to x1 plus derivative of G21 with respect to x2, derivative of G31 with respect to x3, which is, well, G01 is Bx minus del over del T Bx 1 over C plus G11 is 0, G21 is 1 over C derivative of Ez with respect to y minus derivative of Ey with respect to z. So the derivative of G mu1 with respect to x mu is nothing but curl of E minus plus 1 over C. No, sorry, this let me take the 1 over C out, plus the derivative of B with respect to T, the x component. And the Maxwell's equation tells me that this should be 0.
The del cross E term.
So if you look at the second nu is equal to 2 or 3 terms, x mu, you basically get 1 over C, the other components of the curl of E plus del B by del T. X, Y, or the Z components, which would be 0. So now we can write all 4 of our Maxwell's equations. Del G mu nu divided by derivative with respect to x mu should be 0. These give me the 2 Maxwell's equations that do not contain any source terms, that doesn't contain any currents or charge densities. And then we have del F mu nu by del x mu. This was equal to, okay, if nu was equal to 0, minus rho over C, or let me write it this in this form. This is minus rho C over C squared epsilon 0. This is minus mu 0 rho C. Minus mu 0 rho C or J. And these are the other 2 Maxwell's equations. Let's say the new component of this one.
Why derivative of G mu nu should be 0?
That is what the Maxwell's equations tell us. You see, that single equation is equivalent to del dot B is equal to 0, and curl of E is equal to minus del B by del T.
Yes, thought we are going to find Maxwell equations from
No,
this.
we are not trying to find the Maxwell's equations. What we are trying to do is we are trying to write the Maxwell's equations in terms of my rank 2 tensors. We are not discovering them. So we had 4 equations in which time and position, they appeared in a not so symmetrical fashion. We just combine them into these 2 tensors, F mu nu and G mu nu, which just appear to be, in which the time and position appear symmetrically. And then those 4 equations we could write in terms of these 2 equations, where time and position are treated symmetrically. That's the advantage of this thing.
Şimdi hocam burada relativistik bir şey yapmadık değil mi? Sadece tensöre çevirdik.
I mean, what do you mean by doing something relativistic?
Yani bir referans frame'den başka bir referans frame'e göre bir şey yazmadık.
Now, what we did was, we looked at how tensors go from one reference frame to the other reference frame, how rank 2 tensors transform. And when we compared it to how the electric and magnetic fields transform from one reference frame to the other reference frame, we had seen that it just behaves like the components of the rank 2 tensor. So we said that, okay, if electric and magnetic field components, when you go from one reference frame to the other reference frame, if they behave like the rank 2 tensor, we can just treat them as if they are the elements of the rank 2 tensor. So that is how we constructed these 2 possibilities, F and G. Now, if you want to write down how the electric and magnetic fields transform from one reference frame to the other reference frame, well, we know how the rank 2 tensors transform from one reference frame to the other one, so we can just figure it out, even if you don't remember the expressions in the book in terms of the electric and magnetic fields. Just once you remember these tensors, you can just straight away write how they should transform. And then we said, okay, so if we identify the electric and magnetic fields as the components of these rank 2 tensors, so how do we write the Maxwell's equations? Because Maxwell's equations, they are written in terms of the electric and magnetic fields. And what we would like to do is we would like to write them in using F mu nu and G mu, the field strength tensor and its dual. So, and we had seen that if we write the F mu nu and G mu nu in this form, all 4 of our Maxwell's equations can be written as these 2 equations. Of course, each one of these equations is actually 4 equations for each value of nu. So basically here we have 8 equations. Well, in Maxwell's equations, we also actually have 8 equations for each one of the components.
So why do you use only 4 of them? Why do you use only 4 of them?
Which 4 of them?
I mean, now we are using 4 Maxwell equations, not 8.
No, these are 8 equations. You see, this is one equation. This is one equation. This is 3 equations for each component. This is another 3 equations for each component. So 3 plus 3, 6, 7, 8 equations. Here, there are 8 equations written in some kind of a compact form. In this compact form, we only see 4 lines. Here, this is an even more compact form of writing 8 equations.
What are the 3 components of 2 equations who had 3 components?
Well, the x component of this one is equal to the x component of this one. The y component of this one is equal to the y component of this one. The z component of this one is equal to the z component of this one. So those are the 3 equations we have.
So why don't we have the x, y, z components in the, for example, divergence of the, divergence of the...
Because that's the number. You see, divergence of E, this is just a scalar function. It's not a vector. So you cannot talk about the components of a scalar function. Curl of E is a vector. Since it's a vector, we can talk about the x, y, and z components of that. Well, there's still a few more questions that we can ask. For example, I said that this is a rank 2 tensor, which you can just think of as the product of the components of two different vectors. Derivative with respect to x mu is just like the divergence in 3 dimensions. The divergence just behaves like an ordinary vector. So here we have two vectors. We are multiplying with another vector, contracting one of the vectors in f mu nu with this vector. What remains should be a 4 vector. Is this a 4 vector? What about the vector potential and the scalar potential? How will that enter into our description? Okay, that we will do after the break.